Let's dive right into this explainer, where we're going to unpack exactly how engineers finally taught machines to bridge the gap between the visual world and human language. You know, for decades, computer vision and natural language processing were treated as two completely distinct sciences, like they just didn't talk to each other. But today, we're looking at the breakthrough models that finally brought them together, literally transforming pixels and words into one single unified intelligence.
So how does AI actually bridge that gap between seeing pixels and reading words? Well, to understand the sheer magnitude of this shift, we gotta look at the original problem. For years, AI lived in two completely separate, disconnected worlds. On one side, you had vision models. They could identify a dog in an image by looking at edges and shapes. And on the other side, you had language models that could perfectly process the text, letters D, O, G. But there was a major catch. The AI possessed absolutely no way to connect the two concepts. The visual dog and the written word dog were essentially speaking entirely different languages. So the big question was, how do you actually get them to talk to each other?
By building a bridge between these two modalities, researchers unlocked an entirely new intelligence layer that actually gives models three core, very human-like capabilities. First up is perception. And this isn't just saying, hey, there's a dog. It's about identifying exactly what objects are present and precisely where they are based on a text query. Second is generation. This is the ability to produce rich, natural language descriptions of visual content. Think, a dog running along a sunlit beach. And third, which is perhaps the most impressive, is reasoning. This is the AI's ability to answer complex questions that require both visual and linguistic logic combined, like, how many red objects are to the left of the table? Pretty wild, right?
The fundamental breakthrough here was realizing that both raw pixels and written sentences could actually be translated into the exact same mathematical language. If you look at how the image world is structured, raw pixels are mathematically flattened into what we call patch tokens. Simultaneously, over in the language world, sentences are chopped up and mathematically converted into word tokens. Once both the images and the text are converted into these sequences of multidimensional vectors, they can be processed by the exact same transformer architecture. It's basically the ultimate universal translator for AI.
Now, this brings us to a super foundational concept called the joint embedding space. The best way to think about this high-dimensional mathematical space is to picture a giant digital cocktail party. When we project both our image vectors and our text vectors into this massive room, semantically similar content naturally clusters together based on shared meaning. So a photo of a cat and the sentence "a furry feline" will end up standing right next to each other. Meanwhile, totally unrelated concepts, like a picture of a car and the word apple, are pushed far, far apart. So in this space, meaning literally determines physical distance. Moving on to our next section, matching images to text, the Rosetta Stone of AI.
Let's see how all of this theory actually builds into the famous model that made this universal language practical at a massive scale, OpenAI's CLIP. This is where the concepts turn into serious real-world application. CLIP, which stands for Contrastive Language Image Pre-training, completely flipped the script on how we categorize images, turning classification into a brilliant image-text matching game. It works by taking an input image and sending it through an image encoder. Then it takes a whole list of text prompts like a photo of a dog, a photo of a car, and sends those through a text encoder. Both get projected right into that shared cocktail party space we just talked about. From there, the model simply measures the angle between the image and the various text descriptions using something called cosine similarity. Basically, the smallest angle wins the match.
So, CLIP takes what used to be incredibly complex visual classification and simplifies it into a straightforward 4-step recipe for zero-shot processing. Step 1, encode all your text prompts. Step 2, encode your query image. Step 3, compute that cosine similarity. And Step 4, predict the highest match. It acts exactly like a nearest neighbor text search. You don't need to retrain some massive classification head for new categories anymore. You literally just type in a new text prompt and the AI finds the closest visual match. It's really that streamlined.
But here's the thing. To make this actually work, the model needed an almost encyclopedic understanding of the world. To build this robust shared language, CLIP was pre-trained using a contrastive loss function across a staggering 400 million image-text pairs scraped from the internet. Yes, 400 million. It was constantly looking at an image, reading its caption, and pulling them closer together mathematically, while simultaneously pushing away all the incorrect captions in the batch.
And the result of that scale is honestly jaw-dropping. Because of that massive, diverse training scale across those 400 million pairs, CLIP achieved a 76.2% accuracy rate on the rigorous ImageNet benchmark. But wait, here's the real kicker. It did this without needing a single piece of task-specific training data. This is what we call zero-shot learning. It's the equivalent of walking into a final exam for a class you never registered for without even glancing at the textbook and scoring a solid B+ just based entirely on your general knowledge of the world.
Next up, let's talk about visual question answering, or VQA.
So how do we go beyond just matching images to text and actually ask the AI complex questions about specific things it sees? Imagine giving an AI a picture of a dog in a park and asking, what color is the dog's collar? If we use older traditional AI models that rely on something called global average pooling, the model just fails. Why? Well, because those old models essentially squinted the image, blurring all the pixels together into one general dog and park vibe. They lose all the spatial detail. They literally do not know where to look in the image to find that highly specific answer.
The crucial point here is that engineers developed a brilliant solution called the top-down attention mechanism. Instead of looking at the whole image equally, this computes mathematical weights over visual regions. It literally forces the AI's eyes to scan the scene and assign heavy weights to specific areas based entirely on what the question is specifically asking. If you ask about a color, the attention mechanism tells the model to completely ignore the background noise, ignore the trees, ignore the dog's tail, and specifically attend to the neck region of the image to extract the answer. It essentially hands the AI a mathematical magnifying glass.
We can actually see this dynamic focus at play in image captioning too. Take a caption like, a man riding a horse on a beach. When a modern model auto-regressively generates a descriptive caption like that, it doesn't just guess the whole sentence at once. Its attention physically shifts step by step. When it outputs the word horse, its mathematical attention is actively highlighting the animal. When it outputs beach, the attention shifts right down to the sandy ground. And when it says riding, the focus lands squarely on the rider's posture. It's reading the image left to right, object by object, kind of exactly like human eyes darting across a scene.
This brings us to our final section, Next-Gen Unified AI Models. The bridge is built, so what kind of traffic is crossing it now? Well, this leads us to next-gen architectures like Blip. Models like Blip don't just passively match data they're fed, they actually clean up after themselves. They utilize this brilliant self-improving training loop that combines image-text contrastive laws for alignment, image-text matching laws to automatically filter out bad captions, and language modeling laws to generate text. So the model looks at noisy, messy images and captions from the web and automatically filters out the bad, mismatched ones. It effectively bootstraps its own understanding, creating cleaner data for itself to learn from. And perhaps the most exciting application of this is how it transforms basic utilities, like object detection. With traditional detection, systems were limited to a fixed vocabulary of K classes. If an AI was trained to detect 80 specific objects, object number 81 was completely invisible to it. But with cutting-edge tools like Grounding Dino, we finally evolved past that. Because these models deeply understand the relationship between text and images, they use free-form text prompts to locate anything you can describe. You just type in what you want to see in plain text, and it instantly finds it and draws a box around it. It's a real game changer. We've gone from treating pixels and words as foreign, totally incompatible elements to creating a unified mathematical language that empowers models to perceive, generate, and reason across domains. As we continue to perfect this Rosetta Stone of artificial intelligence, and as these models learn to process video, 3D space, and action alongside text, it leaves us with one provocative thought to ponder. If AI can now seamlessly translate sight into language, what happens when it begins to reason about the world better than we do? Thanks for joining me on this explainer. I hope this helps you see the AI landscape just a little bit clearer.